today's lesson is about polar graphing using your graphing calculator. So you'll need to have your graphing calculator out, and we're going to set up a brand new mode. So turn your calculator on, and as you can see in your notes, we're on page 6, and you can see at the top of the page it has all this information on setting up your calculator. So the first thing, we need to put it in the correct mode. So you need to put it in degree and polar mode. So you can see on my screenshot that I've done on here, it's in both degree and polar. So hit mode, and then make sure to highlight degree, which you're used to doing, but chances are yours looks like this, where underneath it says function or func if it's an older calculator. And so if it says that, you need to change it into polar mode. So you'll use the arrow, highlight polar or pole, as you can see on the screenshot, and hit enter. Now it's going to be in polar mode. So to get out, you can hit second mode to quit. So you can see problem 1 is r equals cosine theta. So go to your y equals screen and clear out whatever's in there, and you'll see now you have r instead of y because you're in polar mode. So go ahead and type in cosine, and then you don't have to hunt around for theta. If you use the variable button that you're used to, if you press it, now you get a theta. So exciting. And that's because you're in polar mode. And so we have our equation in there. And now let's go ahead and set up our window. And so on your paper, you'll see that it has these window settings. And so the explanation for that, and we'll go ahead and set that up, so you'll go to window, is what we want to do is we're asking our calculator, the theta min and max and the theta step are what the calculator is actually calculating. So we're going to ask the calculator to calculate values in our equation here for theta between 0 and 360. So we're going to have it calculate one full rotation. Now we need to tell it how often to calculate, and that's where the theta step comes in. That 4 degrees is telling the calculator, calculate at 0, 4, 8, 12, and so on. So every 4 degrees, the calculator is going to recalculate and generate an answer. And so the reason we picked 4 is just because if it's too big, your graph will be really kind of sharp and inaccurate. If you go too small, it's going to take your calculator forever to graph. And 4 is sort of a happy medium. So make sure you include 0, 360, and 4 in your theta, min, max, and step. So that's where the calculator is actually doing work. Now the x min and max and the y min and max, this is your zoom in on your calculator. So the x min and max we have a little bit different from the y. And the reason for that is because look at the window, the actual screen on your calculator. What's going to show is a rectangle. And what we need to do is we want to make our graph appear like it normally would, and so we don't want it to be stretched out inadvertently because of the shape of the calculator. And you'll see it's wider than it is tall, and so what we'll do is we'll make our x min and max a little bit bigger than our y min and max because the x is the horizontal in the direction that it's larger. And the general approximate ratio of our rectangular window is 3 across by 2 up and down. And so that's why we want the distance here to be 3 versus 2. And then your scale is just how often you'll see a little tick mark on your graph. So once you have your window settings matching, like mine, then go ahead and hit graph. And you'll see we actually looked at this equation when we did our transforming polar equations notes on Tuesday, and you'll see that it is in fact a perfect circle, just like we showed in our notes on the previous pages. And so notice if your particular screen is showing an ellipse, if your circle is elongated, you need to go back and fix your window settings. You didn't do the 3:2 ratio, so you probably left your y min and max at -1 to 1. So if you see a perfect circle, that's good. That's what you want. So instead of trying to copy it from there onto your paper, that's going to be really hard. Okay, so we're going to actually use the table, not just copy from the image. We're not trying to ballpark here. We're trying to get as precise as possible. to set up the table, you'll see across the top of these buttons here, you have all these little menus. So table setup is above window. So to get there, you'll hit second window. Okay, and we want to start our table at 0 because we're going to be plotting in our values between 0 and 360. But if you notice on the actual grid, if you look at your paper and you're looking at this grid, we have every 15 degrees. So that's why we're going to do our change in table, the delta table, as 15. Now, to actually see your table, you're going to hit second graph. You can see right above graph it says table, so do second graph. On my screen up here, it's really small, so I've copied all of those values over here, but you have it on your own screen. And so now we need to plot these values on our circular grid. Notice we're graphing cosine theta. And so our R values will never go beyond 1 or -1 because our sinusoid for cosine theta never goes above 1 or below -1. And so we need to set up our scale for our circular grid. Since we're not going beyond 1 or -1, we don't want to make the inner circle 1. It would be really hard to graph, and we wouldn't be able to get the level of detail. So set your scale as 1 for the overall circle. And we're going to use the same scale for 1, 9, and 12. 13 is a little bit different. And so here we're going all the way out to 1, and there are 6 rings, so that means halfway, 3 rings is going to be 0.5. 1.5 rings will be 1/4, so 0.25. And then we can also mark off our 4.5 rings as 0.75, 3/4 of the way out. All right, so now we'll plot in each point. So we've got 0, 1, and that's going to be out here. Then we've got 15 degrees, and we're going out 0.96. So we'll go around 15. 0.96 is going to be really close to 1, but just not quite there. And then at 30 degrees, we're out to 0.866. Well, if this is 0.75, 0.866 is still going to be within this outer ring, so maybe about there. 45 degrees, we're going out 0.7, so that's going to be a little less than 0.75. So I'm going to go to 45 degrees, and we'll be within this second ring, maybe about there. 60 degrees, 0.5, okay, that's exactly 3 rings. And 75 degrees, 0.25, okay, that's about here. And then 90 down to 0. Okay, so you can see we've got a pretty accurate semicircle. Okay, and I'm expecting that on these notes in this assignment, you're plotting very, very carefully. On future assignments, we're going to actually learn how to do this without a calculator, but for this assignment, I want you to practice plotting your points, and we're looking for patterns and precision in what the graphs look like. Okay, so then we have all of these negative values, and you could, of course, go out to 105 degrees, and then negative 0.25, we're going to flip over the pole, so it's going to look like it's on this 285 degree line out about here. Or, for me, it's easier because I know, if I look on my calculator screen, if I look at the graph, I know I'm trying to draw a circle. So I know that there's perfect symmetry here. So if I already have all these points, I'm going to use symmetry to draw the rest. It's going to be faster than going from here. So I did half of them using the actual points, and then the other half, I'm going to just look at my 15 degree, and I'm going to mirror that down here. My 30 degree, and I'll mirror that, and so on. And it makes it a lot faster. Okay, now that I have each point drawn in, then I can go ahead and draw in the circle. Okay, so you'll notice that on these, our grids are in degrees, and we set our calculator up in degrees. But if you're using your calculator to graph and you have a radian graph given to you, I still recommend using degrees, because in here you're going to get all these decimals if you have it in radian mode and you're looking at, say, pi over 6, right? Pi over 12, pi over 6, pi over 4. I don't know those decimal approximations. I'm assuming you don't know those decimal approximations, especially when we get beyond, pi over 2. And so it's a lot easier to keep it in degree mode and then just translate it over. So on your graph, if it says, pi over 6 here, you know that 30 degrees is going to be in the same spot, and it's going to be a lot easier that way. Okay, so now let's take a look at problem 9, where we are looking at r equals cosine 5 theta. So we'll go back to y equals, and we'll switch up, type in cosine 5 theta. Same thing, let's take a look at our graph to start. Now we're getting some petal graphs. The first one was technically called a petal graph, but there was only one petal. Now we've got 5 petals, which you can count. And so we can start this kind of the same way, where we can take a look at our table. So I'm going to just double check my setup. If you've scrolled down at all, you're going to need to restart at 0. So we still want start at 0, change of 15. So now let's look at the table. So when we use these values, we can start the same way. We can go 0, 1, and we have the same scale, r equals 1. And then 15 degrees, 0.25. Right about there. And then you can graph the remaining. I'm just going to graph 1 through 90 or 0 through 90 degrees here. Remember, when you're graphing negatives, they have just flipped over the pole. So 30 degrees and negative 0.866. Well, remember, 0.866 is going to be kind of about here. It's going to be in that outer ring, but closer to that second actual circle drawn. So I'm going to go to 30 degrees, but I'm flipping over the pole. So really, it looks like I'm at 210. And I'm going to go out here for the negative 0.866. And then 45 is going to look like it's on the 225 line. And that's 0.7, so that's about there. And then back to 60, and now it's positive again. So these seem really random and arbitrary. And then 0.96, and then down to 0. So what you'll notice, and if you take a look at your table here, we have a lot fewer 1s than we did on our plain old cosine theta. And the reason for that is, if we look at our graph again, the petal tips are still going out to 1. They're filling in this circle of radius 1, but they're falling in between 15-degree markers. So what we need to do to be a little bit more precise is we need to figure out where each petal tip is going to lie. So we can plot in all of this stuff, but then we also need to think about, well, there are 5 petals in a full rotation of 360 degrees. So we can say, well, 360 divided by 5 is going to be 72. So each petal tip will be 72 degrees away from each other. So if the first petal tip is at 0 degrees, the next petal tip is at 72 degrees. And you are required to label these in. So 72 is going to be a little bit before 75. So maybe about there is where 72 degrees will lie. So then we can add another 72 to get our third petal tip at 144. So we'll go around between 135 and 150, and we'll mark in 144. And we'll keep doing this all the way around the circle. Okay, once we get back to 360, then it starts repeating all over again. It's going to be 360 plus 72, but that's going to lie in the same spot as 72 degrees. So go ahead and fill in each petal tip. Fill in your labels of your degree measures for each of these petal tips. You need to include 72, 144 if it's not labeled on the graph. And include any of the points from over here so that you can complete your petal graph. Okay, so now we have all of our petal tip degree measures labeled along the outside. Each one is 72 degrees away from the last. And we have all of the points from here plotted on the graph. So now we have a little bit more to go on. We can fill in and draw in the rest of the actual petals. Okay, so whenever you're drawing a petal graph, on this handout especially, you need to label in any of the petal tips that aren't previously labeled on your grid. Okay, so now let's take a look at number 12. We'll put that into the calculator, go to y equals, and we're going to switch it. Now we have a sine graph. We have sine 6 theta. Let's take a look at that. Whoa. Okay, so when it was cosine 5 theta, we had 5 petals. Now that we have sine 6 theta, you can see that there are 12 petals. So go ahead and fill in, plotting each of those ones and zeros and negative ones. Okay, and so then from here, if we try to draw any more points in between, I think it's just going to get really, really, really messy. So from here, just very carefully draw each petal. And so you're going to go from the center, always go back to the center, out to the petal tip, and then back in again. And you're trying to not overlap your petals. Okay, so we're also trying to think about where that first petal tip will be drawn. In this case, it's at 15 degrees. Okay, so at this point, go ahead and fill in the rest of your petals if you haven't yet done so. We can see the distance between each petal is now 30 because there are 12 petals in 360 degrees. So problem 13 is a little bit different than 1 through 12. So what we're going to start by doing on this one, if you notice now we have addition and subtraction. So our window settings are going to change. And so to figure out how we're going to even set up our window, we need to do a little bit of math. So what we're going to do is we're going to test points at our 4 main kind of easy degree measures. So we're going to test at 0, 90, 180, 270. And so what we'll do is we'll just plug in. So we're going to look for the point by plugging in 0 degrees. So we're looking at 3 plus 2 cosine theta, so 3 plus 2 cosine 0. Well, remember, cosine of 0 is 1, so we have 3 plus 2, or 5. So we get the ordered pair, r theta, 5, 0. We can do the same thing for 90 degrees, 180, 270, and then we'll have our first 4 points. Okay, so then we need to figure out how to graph these on our grid. We need to figure out what our scale is going to be because we're no longer going to just say that our radius is 1. If we do a radius of 1, it's going to be way too small. And so I'm looking at these and I know that my maximum value is on here. So my maximum radius is going to be 5. We have 6 rings, so there's no need to say the radius here is 5. Make it easier on yourself. So let's just make this entire radius 6, so each ring is going to be 1. So we'll set that up initially. And then we can go ahead and plot each point. So I'm going to plot my first point at 5, 0. Then I'm going to go up to 90 degrees. I'm going out 3, 1, and then 3 again. So now I have my first 4 points. And so then what I'm doing is I need to be able to figure out how to set up a rectangle around this, because it's basically our viewing window from the calculator. Okay, and so we have this rectangle and we need it to be able to fit the entire graph. Now our graph is going to be a little bit round, and we'll take a look at what it looks like once we figure out our window, but this should probably be okay. So I've sort of centered it. It looks like it's symmetric in this vertical direction, so I've sort of centered it that way. Just to make it a little easier, why not, go sort of like that. So it's going out to -6 in the x direction. And so then what we can do is we can kind of approximate where we are. And so to do this, we want to set up our vertical distance first. The vertical is more restrictive. And so we can see that we need to go out, here's 3, let's go out to, say, 5. Or maybe we could reduce it a little bit. We don't have to have it quite this big. We can reduce the size of this and maybe go out to 4 in that vertical direction. Okay, so what we're doing is we're going to set up a little proportion. So what we're going to say is we have our ratio of 2 to 3. Remember, that's the height to the width. And so if we're going to go out to 4, what's the total distance? What's the total span that we're looking at vertically? Well, the total span there, if we're going up and down 4 and 4, is going to be 8. So we're saying that our ratio, 2 over 3, is going to be 8 over, and then we just need to solve this proportion, multiplying by 4, so we can multiply by 4, so we're going to say it's 8 over 12. So what that tells us is that our horizontal direction needs to be a total of 12. So if it's a total of 12, we can try to center it if we want to, but that doesn't really matter. We can just say from -6 to 6. So up here and on your paper, the formatting got a little bit messed up, but you can sort of see where the blanks should have been. We can put in our x min, x max, y min, y max, and all of the scales. So our x min and x max, we can say -6 to +6. The total span is only a total of 12, so we can have a scale of 1. Okay, and similarly, if we're going from -4 to +4 in the y direction, we're just showing what's going to show on the window. That total span being 8, our y scale can be 1 as well. So now we'll go to our calculator and put this in. Okay, so go to your y equals screen, and we're going to type in our function. We'll clear out what was in there. So we'll do 3 plus 2 cosine theta. And so then we can go to our window, and we'll set that up. We've already planned it out. Keep your thetas as is. That's telling the calculator what to calculate, where the x and y don't actually impact the calculations. It's just showing what zoom in we need to display. So we're going to do -6 to 6 with a scale of 1, and then -4 to 4 with a scale of 1 as well. Now we can hit graph, and we'll see what this looks like. Okay, so what we need to do is copy this image over here onto our grid. And again, we need to do it neatly. So we're not just going to eyeball it and draw it. We can look at our table. So we'll go back, make sure we're starting at 0 and changing in every 15, which we are. So now we can take a look at our table, and we can copy down the values from there. So I'm going to use my table to draw in the points. And I'm only going to draw the top half, and then I'm going to use symmetry for the bottom half. Okay, so once I've carefully plotted my points from the table for the top half, now I'm going to go ahead and I'm going to ignore the table for the most part, and I'm just going to copy over. So that one was about there, and so on. So go ahead and complete the other half of your shape, and then connect the dots to form a smooth curve.